Okay, so we're going to start by looking at assignment number 3. To this point, we have gone through all of the information for this particular module. We're looking at velocity analysis, and I'm going to quickly take a peek at our learning plan to just kind of review what we've already covered. So we had a couple PowerPoints. We broke this into 2 lectures. The first lecture, part 1, was looking at how there was a relationship between straight line velocity when we have an object or a link that is rotating. So we established that relationship between straight line velocity, angular velocity, and distance away from the center of rotation. Then we moved on and we started looking at our part 2, which was looking at using the relative velocity method in order to solve for velocities on links that are connected, not directly, but rely on the velocity of another link. So when we have our traditional 4-bar mechanisms, whether it's a crank slider or a crank rocker, we were looking at scenarios where if we knew everything about what was going on the input, if you would, we could then calculate what was happening on the output. So that's what we spent time on the last time we were together. We did work through this handout, okay, and that was really kind of our guide through our lecture. Now, I do have the lectures out there from the first 2 times that we were together and the first 2 parts. And tonight is going to be continuing on and really focusing now on the homework that you have assigned, being sure that you have some good guidance and good templates for kind of finishing up the stuff I need you to know. So we are planning, I'm going to go back to this module, but we'll open up the homework assignment, which is assignment number 3. And what we're going to do is we're really going to kind of relook at the homework. I know we've kind of touched on it and looked at it a little bit, but I want to take it problem by problem and make sure that everybody, feels secure. And if we want to work any along the way, we will. Okay. The first ones here through what's number 12 is going to be based on the first part of our lecture where we were looking at that relationship and for velocity in general, and then also the relationship between straight line velocity related to rotational velocity. And then starting with number 19, this is where we're using that relative velocity graphical method in order to solve for velocities on other links that are in a mechanism. So what I wanted to do was open up to page 161 in our book, and we will start by simply going through each one of these, and then you can tell me if you want to work them out or not. Okay, and then we'll kind of skip over the ones we don't want to go over, but then we'll stop along the way to make sure that we've got some good examples, especially in this relative velocity method. That's the one that's, I think, it's got a little bit more complexity to it. So I think that'll be a good place for reinforcement. So I'm going to go underneath our camera here. And what we're going to do is we're on page 161. So if you want to open up to page 161, I'm going to start by kind of looking at each one of these separately. And again, I'm going to open up our chat box. Feel free to either, just say if you want to see it, or you can put it in the chat. Okay. So the first one that we have here, 6.1, it's a package is moving at a constant rate from one end of a 25-foot horizontal conveyor to the other in 15 seconds, okay? Determine the linear velocity or the linear speed of the conveyor belt. So this is really just looking at velocity in terms of distance divided by time. So I have that equation kind of written up here already. And if you go back to example 6.1 in the chapter earlier, we did have an example that was exactly like this. But does anybody want to? Hi, Nick. I see, Nick, you're coming in. I'll just kind of wait here. Hi, Nick. I see that you're in. I am, I've kind of broken my rule. If you want to turn your camera off, it's totally fine. Just in the way of saving some space on our screen. So everybody else has their camera off, including me. So feel free to do that if you want to. And we're starting at the beginning of our assigned problems on page 161.
Sounds good.
So is anybody interested in seeing problem number 6.1? And I know I had gotten the question before, what do you want the units for velocity in? Since we're in feet and then there's seconds, you can just put it in feet per second, okay? So if there aren't any takers, then we'll look at number 2. Number 2 says we have a hydraulic cylinder. It extends at a constant rate of 2 feet per minute. Determine the time required to traverse the entire stroke of 15 inches. Now here, what you want to do is you want to do a conversion one way or the other so that you can either get the distance that we see here, 15 inches into feet, or the 2 feet per minute into inches per minute, okay, or inches per second. So you want to do that conversion first so that you get consistent units on the distance. And then you can do and solve for the time by rearranging the equation up here, knowing the velocity, and then dividing that into the distance. So does anybody want to see this here as well? What I want to encourage you to do too, required for these problems, because I presume you'll be writing them out by hand. Number 1, they have to be readable, okay? And I'm not super picky, but I do need to be able to read it, okay? Number 2 is you have to show your equation in variable form first. So you would need to, for instance, show this equation first in variable form. V is equal to D over T. It kind of tells me what you're going to be doing. And then you make the next step, and then you put your numbers in where you know them with the units, and then you'll cancel or combine units as needed, and then you'll have your final answer, okay? And it's gonna reflect exactly how I'm kind of doing the steps for you. So if you do it in the way that I'm showing you, that'll be what I'm expecting for the homework that I hand in. I do like to see the work, okay? And some of it you might think is repetitive, or you know, it's too much to show, but at this point, I do like to see that, because it's easier for me if something doesn't match up, that I can give you more points or see where the problem was. If it was just a calculator where something went in wrong, well, then I'm not too concerned if you had everything else set up correctly, okay? But if I see you started off, you know, from the get-go, you know, in a bad way, then we might have to have a conversation, or I'll, you know, make some additional notes and things like that. So it really gives me insights to how you solve the problem. So so please make sure that you write it all out. So does anybody want to see number 2, or does that make sense? Okay. Crickets. That's all right. Number 3, I'm expecting kind of these earlier ones. I know they're easier, and you don't, another reminder is these earlier ones through this number 12, you do not need to draw any CAD diagrams. Okay. It's just going to be with 19 and below. So, so let's look at number 3. Number 3 says determine the average speed in miles per hour of an athlete who can run the 4-minute mile, okay, or a 4-minute mile. So in this case, if you would, speed is going to be the distance, 1 mile, and they can do it in 4 minutes, okay? So you'll notice you would put miles on top, 4 minutes on the bottom, like you see here, and then all it is a conversion to miles per hour. Okay, miles per hour. So so you may need to, if you know, well, the miles on top already, so it's really minutes to hours, so it shouldn't be too tough of a conversion there. And then the next one, number 4, is really going through that same process, but this time they're doing the 100-meter dash in 10 seconds, and they want you to convert that to miles per hour. Now, this time you may need a conversion, and maybe look up a conversion. Feel free to do it online. Just maybe check in 1 or 2 places to make sure it's correct. But you're going to need to convert your meters to miles, okay? And, you know, whether you want to do that in a couple steps, if you want to do it to kilometers first and then convert to kilometers to miles, or directly from meters to miles, if you find a conversion, that's totally fine. Okay. So again, that's another conversion as well. Any questions on that one? Okay. The next one, number 5, is another conversion, I guess. It says we have a gear and it's rotating at 270 degrees in 2 seconds. Okay. They want you to determine the angular velocity in RPMs and in radians per second. So again, it's a conversion. You would take the 270 on top, 270 degrees, per underneath would be your 2 seconds. And then you want to convert it to radians per second and revolutions per minute. Any questions on that one? All right. Well, good. I'm glad. I wasn't expecting a ton of them, but that's good. And then the last one in this first section here is determine the angular velocity in RPMs of the second, minute, and hour hand on a clock. Okay. Any questions on that one? So you're going to do that one 3 times. 3 times. All right. Okay. Now, just because somebody's not asking a question, don't be afraid to ask yourself, okay? Our next one here, number 11, it's actually the statements at the bottom, but the illustrations towards the top of the second column. So we have a drive roller on a conveyor is shown. Determine the angular velocity, so W, of the roller when that belt operates at 10 feet per minute, okay? So if we go up here on the next column, this is going to be the problem we're looking at, or the illustration. So we have a velocity, it's going at 10 feet per minute, and that's a belt that is being, driven by this drive roller, okay? Now this roller is rotating around, and they want to know what is the W here when we have the V, straight line velocity, is going at 10 feet per minute, and we have a radius of half of our diameter. Now, something you want to note here, we know our equation that we need to use, right? But watch your units here. You're going to notice you're in feet per minute up here, and you're in inches over here, okay? So you have to get them in, similar units. Whether you use feet or inches really doesn't matter, because they'll cancel out. And then you're going to be left with radians per second. And then you have to convert this to RPM for your final answer though, okay? So finding W here. Any questions on that one? Okay. No diagram needed again. And then our last one that we have is using that very same diagram. This is a drive roller, and they're telling us that it is going 30 RPMs. So it's going to be going counterclockwise, 30 RPMs. And with 30 RPMs being as fast as that roller is going, what is the linear speed? What is V of that belt? So really rearranging this equation and then solving for V. And then don't forget, radians per second has to be for your W when you rearrange. Okay. Any questions at all on those? You're the same as my last group. Yeah, they were pretty quiet during these. So that's good. That's a good sign. Then let's look at the other problems that we have. So if I'm just going to go over to the assignment here. So the first chunk up here, we just went through, so it didn't sound like there was any need for going over those. So now we're going to focus on the ones down below here. Now, as I look back at my notes and at the video from the last time we were together, we happened to do number 19 and number 27. Okay. So if you do need to go back and watch the videos for those, the video is up there for that now. I forgot to put it up yesterday, and I apologize for that. Somebody did ask about that, and I'm glad that they did. I just kind of slipped my mind. So I did get it up earlier this morning. So if you do need to go back and look at those, but what I want to do then is I want to look at some of these other ones and see if we can, get through a couple of these tonight to get you started and further into the homework, but also ultimately feeling more comfortable with these problems and that relative velocity method. So I'm going to go back underneath our camera, and we are going to look at, we already did 619. So I'm going to let you go back and look at the video for that one. So we're going to skip over that one, but we have number 21 that we could do as well. Now this is a familiar mechanism for us. This is a reciprocating saw. And what we want to do is we want to use the relative velocity method to determine the linear speed of the blade. Okay. The blade, because it's going to be confined to going horizontally, is going to be a slider in our diagram. And we have the crank wheel is going to be operating in a counterclockwise direction this way at 1500 RPMs. So to start this problem, what we need to do is we need to draw our kinematic diagram. Now, you may have this one already we all may have already drawn, because we did see this similar one. I forget if it's this exact same or it might be a little bit different, but what we'll do is I want you to take time to get this drawn in AutoCAD. Now, I have already drawn mine, and I think it is this one, 21, okay? So this is what your kinematic diagram would look like, okay? So I want you to take a couple minutes to make sure that you have this in the form that you need to, using the dimensions that are here on the diagram in our book, because we're gonna have it to scale in the orientation that we see here, so that we then can use our CAD diagram to get the correct directions for each one of the vectors that we need for our vector diagram. So I am going to actually pause the video for a little bit, and I'm going to let you guys, get your diagrams created, and then we'll move on after that. Okay, so now that we have our kinematic diagram ready to go, labeled, and with all of the appropriate links and joints, and then we're using those standard symbols. This is going to be, one of the things that you're required to do for each one of the problems. So now that we have this here and we have it drawn to scale, we are now going to kind of look at the process that we're going to take and then start doing some of the calculations that we need to. I did a quick sketch, of our diagram and added the information from the book. So I wouldn't be, going over the top of the book and drawing on there. And obviously I can't draw on the CAD diagram. So as we look at our problem here, we need to find the velocity of the blade, and the blade is being represented by our slider. Okay. Our slider can only go in a linear fashion. And in this case, it's going to be horizontal. Okay. The crank is going to be going at a rotational speed of 1500 RPMs counterclockwise. And link number 2 is then going to be spinning around. It's going to have an angular velocity. Okay. And it is going to be fixed at this point. Our link number 3, which is the connecting rod, is going to be kind of like, it will be rotating in space, but not at a fixed center. It's going to be kind of like going like oblongish, if you would. Okay. And so it's just going to be, connecting points B and C here. Okay. Now to find the velocity of that blade, that would be represented by point C, which is at the center of that blade. So by finding the velocity of point C and the fact that it's going just in a straight line, that will be the answer to our, problem, if you would. So what I'm going to do is, if we're going in this direction, so this is going to be going this way, that means it's going to be pulling this back, and the velocity of C should be pointing in that direction. We just don't know how long it is, right? We don't know how long it is. So that's what we want to get to, but it's dependent on what's going on over here. Okay. That's why we have to work through this link first to find the straight line velocity of point B, then use our connecting rod to find the straight line velocity of the relative velocity, or the relative link between point C and B. And then that's going to get us to finding the actual magnitude of the velocity of C. Now, we know that the direction of B is going to be, because it's on a rotating link, it's the straight line velocity component on a rotating link. That rotating link is going in a counterclockwise direction. Our straight line velocity has to follow that, but it is going to be going in a straight line perpendicular to the radius back to its center of rotation. So our velocity of B is going to be in that direction, perpendicular to that link. Okay. And then the last velocity that we need is going to be our, and I'm just going to put it like this because we really don't know if it's going, up and to the right or down and to the left. And this is going to represent the line of action for the velocity of C relative to B. Okay. Now these letters all mean something to us, but let's kind of go back to the velocity equation for relative velocity in its like generic form. So we start with the velocity of the unknown is going to be equal to the velocity of the known quantity plus vectorially the velocity of the unknown relative to the known. Okay. And that's really in a very generic sense. So now what we do is we start looking at our diagram and lining up what velocities go where. Okay. So first of all, the unknown velocity that we're going to try to get to is our VC. Okay. So VC is going to be over here. Okay. It's going to be equal to, and then our known velocity, although we don't have, if you would, the magnitude of B yet, we can get it because we know the angular velocity of that link, and we know how far away it is, and we have the equation, and we'll use it in a little bit. V is equal to W times R. Okay, W times R. So we'll fill that in a little bit. So we can get the magnitude, and we know its direction. So our known quantity is going to be the velocity of B. Okay. And that's kind of where all the action is starting, right? And then we're going to add vectorially to B the velocity of C relative to B, which is going to be perpendicular to that line connecting B and C. So as we look here and we identify, in our vector equation, knowing that each one of these quantities need both magnitude and direction, we don't know the magnitude of C, but we do know the direction of C. We know that it's going to be along that straight line, and it's going to be going to the right. Okay, based on this rotation direction at this moment in time. Velocity of B, we're going to be calculating its magnitude based on that equation down there, and we know its direction. And then for the velocity of C relative to B, we don't know its magnitude, but we do know its line of action or its direction as well. So as we look here, yes, we have two unknowns in this vector equation, but because we have them separated by the equal sign and there's only one on either side, this is like those equations that we did at the end of chapter 3 when you did kind of just like getting to know vectors. Okay. So this is handleable for us, if you would. So let's go ahead, and before we go back and into AutoCAD and start doing the vector work, let's get our magnitude of the velocity of B. So to get the magnitude of the velocity of B, we're going to have to use the angular velocity of the link that it's on, which is link 2. Okay, so we're going to put the 2 there. And then we also need to know how long that radius is back to its center of rotation, and that's going to be its radius of link number 2, or the distance of link number 2, which we know to be 0.65 inches. Okay. So now what we're going to do is we are going to convert our 1500 RPMs into radians per second. So you want to do that work over on the side, 1500. We're going to do revolutions per minute. Okay, and we want to get that into radians per second. So 1 revolution is going to go down on the bottom. Remember to do up, down here. Don't do the slash. Is equal to 2 pi radians on top. And then revolutions cancel. 1 minute on top, 60 seconds on the bottom. So now we'll multiply across the top, divide by the bottom, and we'll get a value for W2 in radians per second. I'll do it again. Just as a confirmation, did anyone else get 157.08?
Yep.
Okay, good. So now we're going to use that value up in here. Okay. So I'm going to say equal to 157.08 radians per second times its radius of 0.65 inches. I got to sneak it in there. I'm using pen because I think underneath here, my lighting's not great in this room. It's not as bright as it is at school. So I'm using pen because I found that the pencil looked a little washed out. So I don't advise using pen because I can't erase, but yeah, so that's why. So I'm sneaking it in there. So now we're going to multiply those two together. So 157.08 times 0.65, and I get 102.1. And radians times inches per second, that's going to be inches per second. Radians are going to disappear, right? Oh, I should say B. This is the velocity of B. Sorry about that. Velocity of B. Okay, and just one more confirmation. Does anybody else get 102.1?
Yep, that's what I got.
All right, cool. All right. So now this is our magnitude of B. And we know our direction, so we are ready to start establishing and getting our vector equation in order so that we can solve for our unknown, which is the velocity of C. So I'm going to go over to AutoCAD, and using my diagram, I'm going to get my lines of action for each one of these vectors. So I'm going to start with vector B. I know vector B is going to be perpendicular to link number 2, and link number 2 is going in a clockwise or counterclockwise direction, so it should be going down and to the right as we identified. So I did add a layer here. I have a layer for vector and I have a layer for the resultant. Okay, now just so that you know, if you want to watch me do this first, I will give you time to catch up and do this. All right, so if you wanted to just kind of take a break and just watch me do it, I'll give you some time to add these things and get them in order. So I did add a vector and a resultant in 2 different colors just so that I had it. And I'm just going to draw a line, and I'm going to go kind of random length right now. And I'm going to do shift right mouse button to get my object snaps up. And I'm going to go perpendicular to link number 2. So it's going to make a line perpendicular to it. All right. So now that's the direction of B, and I'm going to move it out a little bit. Not that it has to be, but just maybe on the end point there. Okay. And then I'm going to copy this B here, and I'm going to just kind of scooch it down, and I'm going to make sure that this is labeled as VB. So it's the velocity of B. And now I need to get it to its actual length. Now, this is where, when we look at underneath here, you'll notice that I'm 102.1 inches per second. If I would draw that 102 long, it would be way bigger than my illustration. So if we look at the sizes here, we've got 3 inches, we've got, so if I would do, I think 1 inch is going to be a little small. I think I'm going to do 10.2 inches. So what we'll do is we will just divide by 10. So we'll know that we have to multiply by 10 for our final answer. I just want to have something that's a little bit more the size that we have here, so that you can use it and to be next to the diagram when you do your screenshot. So let's see how 10.2 works. So I'm going to go at the center there, and I'm going to draw a circle that has the radius of 10.2. Oh, that's pretty big. That's pretty big. I don't think I like it. I think we're going to go with 1.02 because it would be that long, which is too big. Otherwise, the printing is going to be way too small compared to it. So I guess we will go with, oopsie. So I'm going to go to the center there, and it's going to be 1.021. Enter. There we go. Yeah, that's actually much better. So I'll trim this away here and then get rid of the circle. So the circle radius is only there to get my vector to the right length. And I can put my arrowhead on this because I know this is definitively how long vector B is. Okay. All right. So I'm just going to leave that there for right now. And then I'll move it when we start our vector equation. Now I'm going to do the line of action, if you would, for the velocity of C relative to B. And that's going to be on a line perpendicular to link number 3. So I'm simply going to kind of start a line out here and go perpendicular. And I'm not going to add any arrowheads to this or anything because I don't know which way it's going. Okay. And I don't know how long it's going to be. So I'm just going to leave it just like that for its line of action. And then I'm going to do the very same thing for point C. Now, point C, although it's not, I'm not going to say it's a resultant, but it is the value that we're going to be solving for. So I'm going to give it a different color. I'm going to go line, and starting at the center there, I know that it's going to be on a horizontal line of action like that. Okay. So now I have all of my, line of actions and or vectors kind of figured out. So if I look at my vector equation here, I have B all set. I've got the line of action for C relative to B, and then I also have the line of action for C. So now I want to set up my vector diagram by starting with an origin that is going to represent that equal sign. So I'm going to go back on my object layer. I'll kind of go down here to create it. I just want to create a nice little crosshairs here. Always do an origin. Okay. I need to know where you're starting. Okay. I need to know where you're starting. I know some people have been leaving the origin off, but it looks like a continuous loop of lines then. So, so make sure you're always putting in an origin. That is required. And I'm going to move my VB, and its tail is going to start at the origin here. I'm going to turn my ortho off now. It's going to start at the origin, okay, because it's the first one in my vector equation. Then on the endpoint of VB, I'm going to add the velocity of C relative to B. So I'm going to move this line, and I'm going to go like nearest here. I don't know if it's going to go up, down, left, right. And then I am going to label that so we know what it is. C relative to B. Okay. And now I'm going to take and I'm going to move my velocity of C. I got to get to the endpoint though. Okay. And that's going to be at origin here. And oh, look at there. I have an intersection, which is exactly what I want, right? So now what I can do is I can trim away the excess here. Okay. And I need to add my arrowheads. Okay. So I'm going to grab my vector. So as we look at our vector equation, we added to the end of B, C relative to B. So that means that C relative to B tail is going to be at the tip of B, and then its tip is going to be on the other side. And then for velocity of C, its tail is going to start at the origin, but its tip is going to go to that last vector on the other side of the equation. So right here, I'm going to add in my lines for my arrowhead here. Okay. Then I'm going to switch this to resultant and do the same thing for that one. Kind of make them a little bigger so they look a little different. Okay. All right. So now, I need to add VC. Make sure you label all of your vectors. You don't have to put in all the dimensions except when we need one. So for this case, we do want to have the dimension for VC because we need it to solve our problem, right? So, so this one we will add a dimension to it. So I'm going to go to the notes and I'm going to go to a linear because it's a horizontal dimension from there to there. And look at that. There is the, there's my value. Okay. Now my value though, we know that we have to multiply it by 100 because when we drew our vector in CAD, we actually drew it to 1.02 instead of 102. So we divided by 100 to get that number. So that means that now our final answer for the magnitude of the velocity of C is going to be 0.9935 times 100. So to write our final answer, we would simply say VC is equal to 0.9, well, what did we say it was? 0.9, what, no. I didn't want to do that. It's going to be 9, 193.5, and our units are in inches per second. Inches per second. Okay. And then this would be your final answer. Okay. And then you can say, you know, from CAD diagram or something like that, because that's where it's from. All right. So now, and I should ask, if anybody was following along, did you get the same thing as me?
I think you're off by a decimal. It should be like 99.39.
Oh, yes, right. It's times, I'm so sorry. Yes. I was talking, it's supposed to be 99.35. Does that sound right? Yeah. So
Yeah.
0.9 times 100, move 2 places. You're correct. Thank you for that. So 99.35 is going to be in inches per second. Thank you. So what I want you to do right now, I'm gonna stop the video and let you catch up with the diagram as well as the work here to finish up that problem. Okay, so I'm gonna pause our video for a couple of minutes and then we'll be back. Okay, so to kind of finish up here, I want to just show you what you would be responsible for handing in for this problem for me to see the work to show that it's complete. So first and foremost, you're going to do a screenshot of your kinematic diagram and your vector diagram. Now, if you want to put these in the same screenshot, that's great. That's what I've been trying to do to kind of keep everything proportional. So that's why I scaled this in that case. Or if you wanted to do separate ones and keep them at, you know, units of 1 to 1, that's totally fine too. But I do need to see your kinematic diagram for the problem, as well as the vector diagram with all the labels that we see here, okay? And the only dimension that you need is anything that is a final dimension for solving the problem or something that you're going to need to, you know, continue on. So that's going to be a screenshot there. Then as we look underneath, the work as far as what we did that you'd be responsible for showing is going to be like below the line here. Okay. I did this illustration so that I could mark up on it, but writing out your vector equation required. Okay. Showing the work to calculate anything that is a known variable required. Any of your conversions are required. And then your final answer with a box around it is required. Okay. And like here, you know, because our answer said 0.9935, you know, multiplying it out and then just putting a little note from the CAD diagram. Okay. So if you have a VC here, if I go to the CAD diagram, I should see VC labeled here as well. Okay. Any questions about what to hand in for this? And this will be really the very same thing for all of the problems. Okay. All right. Again, no news is good news is how I take it. So if anybody does have any questions, don't hesitate to ask. So let's go back underneath and look at the next problems that we have. Okay. All right. Our next problem is going to be number 23 here. This is a shearing mechanism in the configuration shown. We want to determine the linear velocity of the blade as that crank rotates clockwise at 100 RPM. So this is going to be going in this direction here. And we want to know what is the blade doing at this moment in time. Now, this is another crank slider mechanism, just like 21 was, or yeah, 21 was. So really the exact same process is what you're going to go through here, except different numbers. Okay, different numbers. Does anybody want to see this one, or do you feel good about the process that we just did, that you could follow that along and then adapt it to number 23? But does anybody want to see this one? Don't be afraid to say yes. Okay. And just remember, the first thing you're going to start with is a kinematic diagram. Okay, kinematic diagram first. Then you're going to move to your vector diagram, identifying what you know, what you don't know, then calculating anything that you need to, doing your conversions, and then going over to CAD and doing the vector diagram work using the original kinematic diagram for your directions. Okay. All right. So if there's nobody that wants to see this one, then we're gonna peek at the next problems. Now, the last time we were together, we did do number 27, but I know that that's when all the information was new. 28 is the same problem using the same diagram, but different numbers. Does anybody want to see number 28? And number 28 is a slashing bath is used for the to wash the vegetables. For the configuration shown, use the relative velocity method to graphically determine the angular velocity of the water bath as that crank rotates 75 RPMs in a clockwise manner, so the opposite way. So we're really very same diagram, except we are rotating in an opposite direction, and then the RPMs change on that crank, and we want to know, okay, what's the angular velocity of this? Does anybody want to see number 28?
So when I did that one for the velocity of C,
Yes.
I got really close to your answer.
Yeah.
Like, but I'm not sure if it's like
Close
a
enough.
problem.
Oh.
Like yours was 611.49 millimeters per second. And I'm at 611.38 millimeters per second.
For C, what was your number again?
For the velocity of C, I got 611.38.
Oh my gosh, no, you're totally fine.
Okay,
Totally
all right.
fine. Yeah, as long as you're not like 620 or 640. If you're hanging right there, oh yeah, you're on. Yeah.
Okay.
Totally fine. I'm sure it's maybe even rounding, somewhere along the way. Yeah.
Yeah. Okay.
Yeah. No, you're good. You're good.
All right.
And so does anybody want to see number 28? So I'm kind of showing you this, which I did show you last time as well. There are the final answers here for you and intermediates kind of along the way to make sure that you're on the right track. And if your answer is nice and close, I don't even know what I would say is a margin, but especially if it's a decimal, you're good. Okay. But you don't want to be, off. You don't want to say, oh, 620 is fine for 611. That would be too far off. Okay, so I'm going to go back over here. I'm going to ask one more time, 28. Does anybody want to see 28, or you feel comfortable using 27 from the last time to help you with that one? Okay. All right. Then I don't want to waste anybody's time. That's not what I'm here to do. So the last one that I do want to do, these two go together. 31 and 32 are kind of like what we've been doing. We were going to use this illustration right here. And we're going to do 31 to start off with. There's two things that are different here than the other problems that we've been doing. So the first thing is that they want us to determine the angular velocity of the handle or the crank, if you would, knowing that we want the blade to go down at 3 millimeters per second. Okay, we want the speed of that blade to be 3 millimeters per second going down. And they want to know, okay, what's the angular velocity then of that crank in order to achieve that? Now, this is actually more practical problem than any one of the others, because many times that's exactly where we're starting with our design. Like, what do we need it to do? And then you work backwards. Okay, so we need this to be 3 meters per second going down, 3 millimeters per second, I'm sorry, going down. And then we want to know, okay, what's the deal on here? The other part of this problem that's unique is that we have a point X, a point of interest out at the end of that handle. And we need to know what is the velocity, the straight line velocity of X. Okay, so that's going to be one extra thing that we have to do here, okay, that we didn't have to do on the others. So what we're going to do is we're going to start by drawing our kinematic diagram here. So the blade is going to be a slider, and then it's going to be connected to the handle here. Okay, so I'm going to pause the video so that you can pull up AutoCAD and start your diagram. Okay, and start your diagram. So I'm going to pause. All right, now that we have our kinematic diagram all set, okay, we are now going to start on kind of getting prepared and looking at the process that we're going to go through. So we know that our slider or our blade needs to be going at 3 millimeters per second going down. And we're wondering, what is the W2? What is the angular velocity of link number 2 in order for that to be possible, okay? So knowing the speed that we have to go to here, then we have to work through our connecting rod here and figure out what W2 is. Now, to find W2, or the angular velocity of link number 2, we need to know what the straight line velocity is of a point on there. And the one that we're going to use is going to be velocity of point B, okay? So the velocity of point B is a radius away, a certain distance away from its center of rotation. So when we look at calculating for W2, we're going to need to know what that velocity of B is, which we're going to find through our vector diagram in a bit. But we're going to need to know our radius. And I believe from our diagram that radius is 60 millimeters. So our vector diagram is going to get us the magnitude of our velocity for point B, and then we're going to divide by 60 millimeters, which was reflected in that distance away from the center of rotation, okay? So to get the velocity of B, then we need to use that relative velocity equation, where we have the velocity of an unknown is going to be equal to a known plus vectorially the unknown relative to the known, okay? Our familiar kind of standard variables here. And now we want to fill in and we want to identify what is known and what is unknown. So our known is going to be our 3 millimeters per second going down, right? So that's going to be our VC this time is going to actually be on the right-hand side of our equation, okay? So it's a little bit different than the other ones that we've looked at. And then it's going to be plus vectorially the velocity of the unknown. Our unknown is going to be the velocity of B, okay? So this is going to be the velocity of B relative to C this time. The order of these letters matters. The order of those letters matters because we have to say what our unknown is relative to our known. So it always starts with this one, then that one, okay? So if you say, oh, C relative to B or B relative to C, it doesn't matter. It actually does, okay? It actually does because we are finding the velocity of an unknown relative to a known, and it's going to be through that link that we get there, okay? So this is going to be the vector equation that we're going to use. Now, I always like to take inventory to be sure that even though we have some unknowns here, we want to make sure that they're separated and having no more than one on either side of the equal sign. So if we look at velocity of B, the velocity of B, we know we don't know the magnitude, okay? So that's unknown, but its direction is still going to be perpendicular to the radius back to its center of rotation, and it's going to be pointing, you know, down and to the left because the rotation is going in a counterclockwise direction. So VB, we do know direction, we don't know magnitude, okay? And then we already know magnitude and direction for VC. We know it's going to be 3 millimeters per second going down. And then the velocity of B relative to C is going to be on a line of action that's going to be perpendicular to the line connecting B and C. So this is going to be the velocity of B relative to C. Okay. So this all really kind of is familiar, except this time our variables are in a little bit different order because of what we know and what we have to find. Okay. Now, we don't have to do any work down here to calculate anything because it's a straight line velocity and we know it's going down, okay? So there's no VB work down here like we had to before based on a rotating link, okay? We'll get to do that after we get our value for VB because we're gonna have to use it to find our final answer, which is going to be the rotational speed of link number 2, okay? So let's go over to AutoCAD and let's set this up. So based on our equation, we know that we have to get our velocities in place. And what I like to do first is to get my lines of action of each one of the vectors I'm going to be dealing with. So, so first and foremost, we're going to put our velocity of C going straight down. So I'm going to have a line that's going to start right in the middle there, and it's going to go straight down. Now, because this is only 3 millimeters, okay, and everything else is bigger than that. What I did the last time I worked on it, I actually scaled in the opposite direction. I'm going to draw this at 30 millimeters long, so that it actually shows a substantial length rather than a really short stubby little line. So, so I'm gonna go directly down and I'm just gonna put 30. So again, it's representing 3 millimeters per second. If I would do 3, it would be teeny tiny, okay? And then I can put my arrowhead on the end here because I know definitively that that is its length. And I'm going to put this down here and we're going to call that, see, VC, okay, velocity of C. There it is. The next one I'm going to do is going to be the velocity of V relative to C. So I'm going to do the line and I'm going to go, maybe I'll start here and go perpendicular to link number 3, which is going to be the direction for the velocity of V relative to C. So I'm going to copy this and rename it V relative to C. Okay, no arrowhead there because I don't know left, right, up, down, that kind of thing. The last one I'm going to do is going to be for the velocity of V. I know it's going to be perpendicular to the radius back to the center of rotation for point B, and that's this back line here to the right, not the front one. Okay, it has to be this one right here. So I'm going to draw a line, and actually I'm going to do it green because B is going to be what we're going to be solving for. So I'm going to do a line and perpendicular to here. Okay. All right, and then I'll add my arrowhead when we get our vector diagram going. So over on the right-hand side here, I'm going to start my vector diagram with an origin. Remember, that is required. Okay, so I'm going to go down ortho. And I'm going to start. Let's go back at our vector equation. We're going to start where we know the most, and we know the most with VC. So on this side of the equation, and then we're going to put VC in place, and on the endpoint of VC, we're going to put the line of action for V relative to C. Okay. So I'm going to move, and I'm going to move it. I'm not going to leave, anything here. I'm not going to copy it. I'm going to simply move it. I want to be at that endpoint there, and I'm going to go to my origin. Okay, because the only reason we need that. Well, we need the kinematic diagram to kind of identify everything for us, but ultimately it's for the directions of each one of these. So there's my VC. On the endpoint of VC, I'm going to move and I'm going to put this right there. Okay, and then now I've got the right-hand side of my equation done. Okay, right-hand side of my equation done. Now I'm going to go and I'm going back to my origin. So the tail of VB is going to start at the origin, and then it's going to have to point to the last vector. So I'm going to move this, and I'm going to take the tail and I'm going to put it right there. Okay, and I have to label it. So let's get that labeled. And this is VB. Okay, so now I've got to get my intersection here. So if there's not, the intersection created, so this would have to be extended and then trimmed. Something that you can use is the fillet function with a radius of 0. So if you click on fillet, and you'll notice down here, I can select or key in R for radius, and it's going to tell me what the default radius is. And when you go into AutoCAD, the default radius for fillet is always 0, and that means it's making a sharp corner. So I'm going to accept that by just hitting enter, and then I'm going to click on these 2 lines to get it to be a sharp corner, and it's trimmed at the same time, which is nice. I do have to trim back this one. Okay, and now I have my my lengths, but I do need to add my arrowheads. So I'm going to add the arrowheads to the endpoint of B. Now B is going to start its tail at the origin, and it's going to point to the arrowhead of the last vector, which is going to be here. So I'm gonna put this one in place. So this is gonna be my VB. And then my arrowheads for B relative to C, this is adding tip to tail. So the tail is gonna be on the tip of C. And now I'm gonna add the arrowheads for that one. There we go. Okay. So now the last thing to do is to add in the magnitude for VB, because I need that for solving for W2. So I'm going to do an aligned dimension because it's not horizontal or vertical. So endpoint to endpoint, and I get 31.88. 31.88. Okay. Now, when I look at this number, remember, we multiplied 3 millimeters per second times 10 to get it so that it was a decent size to be able to see. So that means that I need to divide 31.88 by 10 in order to get its final value. So the velocity of V is actually going to be 3.188 millimeters per second. Okay. So now I'm gonna use that. VB is equal to 3.188 millimeters per second. Okay, and that's going to be from CAD or from the vector diagram. Okay, now I can use it. Okay, I'm actually going to redraw this down here. So I know that my equation W2 is going to be equal to my VB divided by my R2. So now I know my VB is 3.188 millimeters per second, and I'm going to divide that by 60 millimeters. Okay, now I'm going to let you finish this up, okay? And we're going to check back in just a minute. So I'm going to pause the recording. I want you to work on finishing up the vector diagram if you need to. Okay, I want to give you that time to do that. And then also get started and actually finish this equation here, and we can compare answers in a bit. Okay, so as we look at the calculations here, solving for W2, which is going to be the rotation of our handle as velocity of B pulls down and to the left at 3.188 meters per second. Okay, from our diagram here, we did have it at 31, but remember, we drew it a little bit bigger, 10 times bigger, so that it would actually show up on here. So our VC is actually drawn at 30. So everything is here is scaled up by 10. So we had to divide by 10 to get our actual value of 3.188 meters per second of B. And at that velocity, our W then is going to be that value for VB divided by its distance away from its center of rotation. So this R right here, which is 60 millimeters from our problem. Okay. So you should get 0.0531 radians per second. And then as a final answer, we always have to convert it so it's in RPMs, okay, RPMs. And then because of the direction of VB, the rotation then is going to be going in a counterclockwise direction, which we anticipated and had drawn it there earlier, but confirmation. And you want to make sure that you also add the direction that it's rotating in. That will fully define a rotational speed, okay? Any questions here on W2? Okay, if not, then there is a second part to this problem, okay, which is unique from the other ones. What we need to do is determine the linear velocity of point X, the linear velocity of point X. So point X is on link number 2 on the very end of the handle, okay? We want to know what is the linear velocity of that. Now, the process to do that, okay, it's just like any other point on a link. What we need to do is we need to determine its distance from the center of rotation, okay? And the way we get that is to draw a straight line to the center of rotation, because right now, if you look at the handle, there isn't a straight line going to it, but it's still going to be its radius, even if it's not actually, you know, part of the link, if you would. So the steps that we're going to take in CAD is we're going to draw a straight line back to point A from point X. Okay. And then we're going to measure this. Okay. We need to know what is the radius of that, or what is that distance? Okay. because to get our Vx, we are going to use the rotational speed of W2. So this is going to be W2 times that distance, or the distance back to the center of rotation for point X. Okay, then its velocity will be perpendicular to the radius back. So not any of these lines here. It's going to be that front line right here. And that is going to be our value for Vx. Okay, Vx. Now I'm going to just take a peek here really quickly at our answer key. Okay. All right. So we just want to know what the length is. We just want to know what the length is. Okay. No problem. Oh, I'm sorry. Yeah, Vx. We just want to know what the length is. We don't have to. I was going to see if I had in there the angle, but we don't. That's okay. So let's go ahead and do this process in AutoCAD. We're going to add that information to link number 2. So I'm going to go back to my object line layer. I'm going to add a line. And I'm going to start at the endpoint here. And I'm going to go to the center. I got to make sure I get on the center right there. Okay. And now that establishes that radius of X back to its center of rotation. Okay. I also need to know how long it is for my calculation. So I'm going to go to my notes, align dimension from here to here, and I'm going to pull this out over here. Okay. So it's 250.71 millimeters. Okay. And then the direction of my velocity, and although I don't need to necessarily know or what its angle is, but my vector would be direction-wise line perpendicular to that. Okay. Now I'm going to put this on its endpoint because we're going to label it and draw it to scale. Okay. So let's go back underneath here. Once we get it calculated, we're going to calculate our value for Vx. Okay. So W2, we need to have that in radians per second. So down here in our calculation for W2, it's probably better to put it down here. Why don't I do that? So I'm going to do Vx is equal to W2 times R2. Let's put it down where all the rest of the work is. Or Rx, sorry, the distance of X from the center of rotation. So we know this is our value in RPMs, but remember, we got it first in radians per second. So we don't have to do any converting. We can just use this value right here. So this is going to be equal to 0.0531 radians per second. Okay. I'm going to put parentheses around that times that distance. So that distance from AutoCAD was 250.71. Now this is the actual value because that wasn't the velocities that were scaled up. That's the actual length that we see. So 250.71 millimeters. Okay. So when we multiply those together, radians times millimeters, radians drops out, and we will get a value of 13.31 millimeters per second, and that's going to be equal to Vx. Okay, Vx. So what I'm going to do now is using that number, I am going to draw it on the diagram. Okay. 13, let's see. So 13.31 times 10. We want to multiply it by 10 so that it's consistent with the scale that we used for the vectors. So I'm going to do a circle here, and my radius is going to be 131.1. So I'm going to extend out here. There we go. And again, it's scaled up by 10 so that it represents and it is in same proportion as the other vectors that are on here. So then now I'm going to put my arrowheads on. Okay. And then add a label. Let's grab this one, call it X. There we go. Okay, so make sure that's on your diagram, perpendicular to its line back. Make sure that this dimension is on there, the 250.71, and that this is drawn to scale with its arrowhead going down and to the left. Okay, now as far as handing in, then this would be your screenshot, including the VX. Okay, and then we would go back over here and I'll zoom out a little bit. Anything below here is going to be the work that you need. Okay. Anything that we did as far as calculations. The diagram up here was mine to kind of draw, and you don't have to do this. If you do, that's fine, but you don't have to add that. Okay. Because you have it captured in the AutoCAD. Okay. So what I'm going to do is I'm going to give you a chance to kind of finish up this problem, and then we will check back in a bit. Okay, so I want to take one last look at the homework problems that we have this evening and kind of, see where we're at. So the very last one that we just did was 631, and it was looking at this hand operated shear. Now 632 also uses this very same setup, except this time you are going to be determining what the linear speed of the blade is when the handle is rotating clockwise at 2 radians per second. Okay, so they're giving you the rotational speed in radians per second already, which is kind of nice. So it's going to be kind of back to that traditional way where you're starting with the crank, the information here, and then working through to the slider, which is the blade. Okay, and then additionally, with that very same rotational speed, you need to also calculate that point X again in that same manner that we did on problem number 31. So that'll be a good guide for you. The next problems are going to be the vegetable bath. The last time we were together, so on the second video, you're going to find the process for solving the angular velocity of the sloshing bath from problem number 27. That same process will be used for number 28, except there are just different numbers. So in this case, your rotational speed of the crank is going to be 75 RPMs going in a clockwise direction. Okay. And so you'll be going this way instead of counterclockwise as problem number 27 did. Okay. But same process. And then when we look back, I'm kind of going in a backwards order at number 23 here. Number 23 is a slider crank again, which is going to mimic the same process that we did this evening for number 21. Okay, not that they go together, but process-wise, they're exactly the same. Okay, so you're going to be finding out, how fast the blade is going and in what direction based on the rotational speed of the crank. Right. And then the last time that we were together, we did go over 619. Okay, so in that second video, in this series, you'll find the process for that. Okay. And then we had looked at on the first page here a number of these, which seemed like you guys were pretty confident in. So that's as far as I was planning on going tonight. Okay. And then taking any questions. I want to remind you as we look at the answer key here, make sure that you're getting the answers that are here. These are just the final answers. So, I mean, you have to show all the work and everything, but at least then if you're on the right track and if by moving to the next problem is what you want to do. Also, make sure that you get these intermediate answers. So I have like the VBs and the VCs along the way before getting to a final answer. Okay, so wanted to make sure that you had that as well. I'm gonna sneak back one level here. You'll upload your assignment, to assignment number 3 here. Screenshots is basically probably going to be the easiest, and then maybe photos or PDFs of the handwritten notes that you do. So I think all the instructions are here. Does anybody have any questions before I kind of let you go? Okay, crickets. That's okay. That's all right. So I am going to stop recording